Hello, everyone. Thanks a lot for attending my seminar. This work is a collaboration among several institutions and among multiple countries. So since one-time password authentication becomes more popular to be used in mobile applications to verify users' identity, so we're quite interested in whether the generated one-time passwords are secure. So first, I will introduce what is one-time password authentication. Give a mobile phone application. A user types in her mobile phone number and sends to a login request to the server. Then the server runs a pseudo-random number generator to generate pseudo-random number, which can be treated as the OTP. So this one is sent back to the mobile phone. By using the OTP, the user can log into her own account. However, what happens if the OTP is predictable? It means that the attacker can monitor the entire communication and predict the following OTP sequences. These OTP can be used to access the victim's account. So here we can learn that the security of the OTP value is one of the essential part of the OTP authentication. Then we would like to figure out what are the potential weaknesses are. First, we study the existing algorithms that are commonly used to generate a pseudo-random number. There are 4 algorithms here. The first one is the LCG. For this algorithm, it uses a discontinuous linear regression. A linear equation, so an attacker can extract a sufficient number of pseudo-random numbers to predict the subsequent values. The second one is a logic Fibonacci generator. The algorithm is an improvement of the LCG. It uses a recurrence relation. However, when we're using 2 seeds, it is still vulnerable to birthday attack. So if we use 3 seeds, it can be, and at least one of them is the odd number, then this algorithm will be secure. So the third algorithm is the MT. It uses a group of permutation and the tampering operations instead. However, this algorithm is based on the linear recursion, which is still vulnerable. So for this part, we analyze the MT199. 37. So this algorithm is only generate 624 unique numbers, and the rest numbers are just repeated. The fourth one is the algorithm similar to MT by using shifting and bitwise operations. But when we give the same seed, the same sequence will also be generated. So this algorithm is also vulnerable. So by analyzing these algorithms, we actually abstract 5 randomness rules that need to be followed. So first, do not use static OTP values. It forbids using a static value for all login sessions. The second one is forbids a sequence with patterns. It contains 3 sub-rules. The first one is do not generate a repeated sequence for OTP value. The second one is do not repeat each distinct OTP value for n times. And which means each OTP value should be unique. The third one is do not generate OTP values with predictable binary representation. So for some institution, we may not be able to identify patterns from the decimal formats, but there are some bitwise and shifting operations when they use the binary formats, so we can analyze the binary. The last one is do not use the constant or predictable seeds to initialize the randomness function. Otherwise, the entire sequence could be predicted when the same seed is being used by the attacker. When we understand the randomness rule, next we figure out a way to identify the weaknesses. So since the pseudo-random number generator is usually implemented on the server side, and we do not have the code of the app server, we will analyze the generator by extracting the generated OTP values. So in total, we have 3 components. We use the authentication locator to filter out the application without using login authentication. Then we use the application. We take the application as input of the request processor. So OTP links will locate the application with SMS OTP authentication and filling a valid number, mobile phone number. and send requests to the app server. So according to the response, OTP links will further use vulnerability detector to analyze the generated OTP sequence. I won't go detail of the OTP links, so you can refer to our paper to see if you are interested in this work. Next, to do our evaluation, we actually collect over 6,000 applications from Google Play and Tencent app. Among them, 3,000 of them are applications with locking activities, and 2,000 of them contains the SMS OTP authentication. After analyzing those applications, we actually found around 400 of them are vulnerable. They just violate the rules that we determined. 41 of them just break the first rule that generate static OTP values, and 20 of them just keep retaining the same OTP values, although those values were consumed. So, which means these OTP authentications are just being used as the same of the password authentication. But such kind of a way is vulnerable because OTP values are quite short. They only have like 4 digits to 6 digits. So this part is vulnerable to brute force attack. Also, we test whether these applications return the same value for different accounts, but fortunately, they just return a different OTP value for different accounts. Next, when we are analyzing the repeated sequences, we found that 162 applications produce the OTP values by generating the repeated sequence. So as I mentioned just now, MT19937, it actually only generates 624 unique pseudo-random numbers. So which means these applications, they actually use this algorithm to generate the OTP. Next, when we're testing the route 2.2, actually 67 applications, they repeat each distinct OTP values for n times, which means 39 of them, they repeat each OTP value twice, and 27 of them repeat the OTP value for 3 times, and 1 of them repeat the OTP value for 5 times. So we just wonder whether these OTP values will be changed after we wait for a period of time. Then after we set the time period, 44 of them, they just renew the OTP values within 20 minutes, and 6 of them, they renew the OTP value within an hour. The rest of them, they don't even update their OTP value, even though we have already consumed that. So in total, although the other OTP values cannot identify any patterns from their decimal formats, we just tried to analyze their binary formats, and we found that 125 applications, they actually have the specific pattern from their binary. 35 of them, they generate OTP values with the shifting patterns, and 90 of them, they generate the OTP values with odd and even patterns, which means there are either 0 or 1 at the last digits of the binary format. Finally, we also found 4 applications that use the constant and the predictable C to initialize the randomness function, which means 3 of them are using srand, the function of srand. This one will generate a constant seed to seed the pseudo-random number generator, and 1 of them is using the timestamp. So finally, we actually analyze the randomness algorithms and functions, and further, based on these algorithms and functions, we generate the specific rules that must be followed. To identify the weaknesses, we just design the OTP link to investigate the randomness of OTP values. And finally, we just post our findings that 399 applications are vulnerable. So here's the end of my presentation. I'm welcome to any question if you got any. Thank you.
Hi, welcome everyone. So we are at the Q&A session for the first paper of this great session on Android security and vulnerability. And Siqi is here with me. She's the first author of the paper, Fine with 1234, an analysis of SMS one-time password randomness in Android apps. So I'm Alessandra Gorla from India Software Institute, and I'm happy to moderate this session with questions. So as with other sessions, I invite all the people who have been attending to post the questions on the chat so that I can read it to Siqi so she can answer. So please start writing questions. And in the meantime, I may start asking a question, because I found the paper quite interesting. First, as an Android user, so I have an Android phone myself, and then also as a researcher. So since I've been quite interested in doing research in Android, so I found quite interesting and scary to see how many applications violate these rules, and some of them seem to be trivial, especially the first one, where you basically say, do not use the same value for this kind of authentication. So I was wondering, for the applications where you found the violations of these basic rules, are these applications popular, or they are maybe not so well-known applications? Can you comment a little bit on that?
Yeah, so for these applications, we actually collect the top 100 applications from each category. And so I suppose that these applications are quite popular. So it is just using by most people.
Okay, well, that's really really quite scary. And I was wondering about the first rule. So the violation of the first rule, where that basically says do not use static values, which again to me it seems quite trivial. The way I understand this rule is and how these applications violate these rules is that basically the applications always returns the values, even if the code has been used already in other interactions. But then in the presentation, you were saying that this kind of use of the OTP values is vulnerable to brute force attacks because the values are short. And to me, we are talking about two different problems. I don't know if I misunderstand something, but I see two problems, and they are all critical. Both the idea that you use something that is a short code, so it's prone to brute force attack, and the other one that is even worse, that is you just keep using the same one. So can you maybe clarify this?
Yeah, so for the static value, we just want to check whether this OTP values can be, whether these OTP values are changed after we consume that. Because if we keep sending the request, we will keep receiving same OTP value. So that's why we call it's a static OTP value. And then I think I mentioned this in my presentation, that once we consume that, the server has already changed. After we consume that, the server changed the OTP value after that. But for the brute force attack, because we know normally because for my previous paper, I also analyze whether the OTP values from the length of the OTP values. So we realized that the secure OTP values will be over 6 digits. But if it is lower than 6 digits, because some of them they only use 4 digits. So if you only use 4 to 6 digits, so the attackers, they have enough time to exploit what kind of static value, what kind of OTP values you're using. They can just crack your the password within a sufficient time. Yeah.
Yeah. Okay. And yeah, Konstantin had a question that I also had. That is usually OTP values is allowed to be typed in just a few times before it's invalidated. What are the possibilities for the brute force attack then?
Sorry, what is the question?
That is, so the question is it really possible to have a brute force attack in this case? Because usually applications, they don't let you make an infinite number of attempts to type an OTP value. So after maybe you type it 3 times, then you have to start again the process. So
yeah, okay. Yeah, thank you. That is also a really good question, because we also mentioned this in our previous paper. So if you're interested in this part, you can also refer to our previous paper. So in that paper, we realized that a lot of applications they actually set up the 20 limited times, so or unlimited times. They do have the unlimited times of attempts. Yeah, so it is possible
for another problem.
Yeah, it is actually possible to for a brute force attack. And also, actually, if you want to crack the password, you can also try that offline. So you can try, you can try to crack it and then send it back to the server.
Okay.
Yeah.
And then another question is, do apps usually use their own implementation for OTP, or they rely on third-party libraries? What is your experience, or if you looked into that?
I'm sorry that this question, I cannot answer that because we don't have the source code from the server side. So okay. I'm not really sure about that. Yeah.
Okay, but can't you? At least you could check the APK of the application to see if somehow the generation of the OTP value relies on some kind of third-party library, or it's just implemented from scratch.
The generation is actually conducted on the server side, but in our experiment, we actually test all the random number all the functions for generating random number. So these functions are standard functions provided by C or Python or Java. So I suppose that what we found here should be provided by standard. Yeah. Right. Yeah.
But you're right. Now that I think about it, it's kind of hard to answer this question because you would need to have more information on the server side.
Yeah.
Okay. We have less than a minute, so maybe I can go for another question. So I was wondering, about the rule 2.2 that says do not repeat each distinct OTP value. I was wondering, because sometimes you saw that it was used even up to 5 times. I was wondering how many runs did you do for each application?
Sorry, I cannot remember the detail of the. I think Sorry, that I cannot remember the detail of
No problem.
of this
And
part.
we are actually already out of time.